Hi, this is what you were taught an atom looked like. Wait, there's 3 protons. So this is an ion. Because there's 5 electrons. Crap. Anyway, let's just add more protons then. That's an R. What the? Anyway, this is what you were taught that an atom looked like when you were in school. You have your protons and neutrons in the nucleus. This is the nucleus, nucleusi, and the electrons going around the atom. Well, what if I told you that inside of protons and neutrons were smaller particles? They're called quarks. No, not bottle corks, idiot. Subatomic quarks. Yeah, they're spelled quarks. So let's learn about quarks and stuff. A proton is made up of... Oh, wait, this is out of focus, frick. Oh, my God. Oh, Lord. Okay, so... a proton is made up... Oh. Okay, so there are 2 kinds of quarks that you need to know about right now. There's up quarks, and there's down quarks. They're the same size, it's just... they both have... well, the up quark has a charge of positive 2/3, and the down quark has a negative 1/3. So... and a proton is made up of an up quark, another up quark, and a down quark. So, that's 2/3 plus 2/3, which is 4/3, then minus 1/3, which makes 3/3, which is equal to 1. So that's why a proton is 1. Now, you're probably wondering why the heck these things stick together. Well, shut up, I'll get to that. Next, this is a neutron. I have no idea how to spell this part. Because it would sound like it would be this, but no. Anyway, a neutron is made up of a down quark, another down quark, and an up quark. 2 of these and 1 of those. So positive 2/3 means that's 2/3, and then... no, positive 2/3, and then negative 2/3, which is this, because negative 1/3 says negative 2/3, and they cancel each other out, so that's why this is a 0 charge, neutral. That's why it's called a neutron, because it's neutral. So, what do you think an electron is made out of? Okay, I'm just reminding you, this is negative 1/3, positive 2/3. This equals 3/3, so that's 1. This equals 0, so that's 0. And this equals... what is that? What quarks are in an electron? Just, I'll let you, think of that. Ow. So, an electron is made out of, drumroll please. Okay, an electron is not made out of any quarks. Got ya! It's so let me just go over all the particles here. Now these are called fermions because they have a spin of 1/2. So there's an up quark, a down quark, and an electron. These are the particles that make up an atom. Now, there's something called a neutrino that's like that. That's an electron neutrino. This is the first generation of matter. Now, these two guys are called leptons. And these are called quarks. These are leptons. That's a neutrino, that's a normal lepton, and these are quarks. So, there's a second generation of matter. There's a charm quark that also has a positive 2/3. All of these have a spin of 1/2 also. Then there's a strange quark, and then there's, sorry, I don't know why I'm so shaky. Then there's a muon. No, that is not a weird U that I just drew. That is the lowercase Greek letter mu. That's why it's called a muon. Ha ha ha. Then there's a neutrino flavor of that. They're called flavors. I don't know why they called them flavors. But anyway, yay. There's a neutrino version of that also. So, these are neutrinos, the normal leptons, and the 4 quarks so far. The neutrinos are resulting in sometimes bigger particles. The reason these particles don't stay for very long is because they are fat and they decay quickly, and sometimes neutrinos come out of that. So they also come from the sun because there's a lot of fusion crap going in the sun, and neutrinos are very small. They are the smallest thing, the smallest piece of matter that we know of. So then there's a third generation of matter. Dang it. That was a lead that fell. Anyway, there's a third generation of matter. There's the top quark, which is too fat to fit in, because there's like up, down, strange. That can happen. That's called a lambda baryon, because baryons are particles with 3 quarks. But top quarks are too fat to fit in a 3 quark group. And I'll get to why they stick together in a minute. But top quark. Then there's bottom quark. This is positive 2/3, negative 1/3, negative 1/3, and positive 2/3. And that's what the thing is. I'm gonna put a new there for neutrino. Anyway. The top and bottom, and then there's the tau neutrino, and this is not a T, this is a tau, the lowercase Greek letter. And then the tau neutrino. Okay. That is all the fermions. So, yeah. So a second generation thing, I guess, would have, yeah. Now, these things are weird. First of all, I'm just get this off. There's these things called mesons, and they're a quark. That's an antiquark. A quark and an antiquark pair. And they just stick together and evaporate. Sometimes they like pop in and out of quarks, and all of these particles pop in and out of existence all the time. But so this is a meson, and yes, antimatter does exist. It has been proven to exist. but it has not been found in large quantities in the universe. But when they touch each other, they'll just blink out of existence, because when antimatter touches matter, it releases when they cancel each other out, they release a massive amount of energy. So that's why if you touched a normal atom with an anti-atom, that would make like a super frickin' antimatter bomb. I don't know why I added the super frickin' in there, but you know. Anyway, back to the hadrons. Well, no, these two are hadrons. A hadron is a group of quarks. Back to the baryons, the lambda baryons, up, down, strange. But anyway, there can be an up quark, and another up quark. That's called a double positive delta baryon. This is also a delta baryon. This is another delta baryon, and then there's a down, down, down. Like how I did then, haha. That is called a negative delta baryon. So, the names for these baryons is kind of weird. A delta baryon is a baryon made up of normal matter, up quarks. Then there's, I don't know why I drew a line there, but delta baryons are made up of normal up quarks. Then there's sigma baryons, which are made up of it can either be two up quarks or two down quarks, or an up and a down quark, and then it's one of these. And if it's a strange quark, you put the charge right here if it's positive or negative. And whether or not if it's strange, if it's a strange quark that's in there, you don't need to put that for some reason. And then if it's a charm quark or a bottom quark, because remember, it can't be a top quark because top quarks can't exist. But if it's a charm quark or a bottom quark, you have to put that there. So charm or bottom or whatever. Anyway, if it's then there's a xi, spelled like this, because this is all Greek. This is a xi. And a xi baryon has either an up quark or a down quark, or anything, I'm pretty sure, I don't know. No, just an up quark or a down quark, and two of these things. And then an omega has all three. Has no up quarks or down quarks in it. It's just that. So, now that we got the baryons out of the way, we can focus on the next set of particles called bosons. Now, there's 5 bosons that have been discovered so far, the first of which is the gluon. Now we get back to what... oh, I'm dumb. The bosons are force-carrying particles. So, what holds the quarks together in a baryon? So, let me just draw a proton here. And the gluons... Now, the quarks come in they come in those 6 different flavors, but they also come in 3 different colors. And they're not actually colors, they're just called colors because there can be a green, a blue, and a red. Those are the only 3 colors that you can see. There's no yellow, orange, purple, pink. It's only green, blue, and red. That's it. Those 3 colors together, red and blue make magenta, so that's the opposite of green. Green and red make yellow, and the wavelengths of green and blue make cyan. And all of these colors combined makes white light, and that's why we call it color, because you never find a quark alone. It's always in a pair. But they always change colors. And when they change colors, it's kind of like color charge, like except if if electromagnetic charge has positive and negative. This has 3 different charges: red, blue, and green. So you always find them in pairs of 3 because they attract each other. They attract the other 2 colors, but they don't keep their color. They keep changing their color. So they would just go away off into nowhere. So that's what this gluon, they stick these together. It is the strongest force in the universe. It's called the strong nuclear force. And it's not called strong for no reason. It is the strongest force in the universe. It has to hold these 3 things. The gluon bounces around from each thing, just changing their color charge and keeping them red, green, blue. It keeps their color charge the same because the quarks keep on changing. Or maybe the gluon. Yeah, the quarks keep on changing their color charge, but the gluon keeps it the same. And then, I don't know, you can look at the 4 fundamental forces by Joe Scott on YouTube. He explains that there's a meson called a pion, which is that, I think, an up quark and an anti-down quark. I don't know, that's a pion. But that thing can get created inside the proton and then just zip off to a neutron and swap the up quark or something. I don't know. You can watch his video on it. He explains it a lot better, and there's a diagram that shows it. But that's what keeps the pion, keeps the neutron and the proton together. That's why the nucleus of an atom, that's why neutrons are sticking with protons. Now, this, the gluon is the whole reason any of it is stuck together in the first place. So, the gluon is pretty special. Now, on to the next boson. We have a photon. That's the symbol for a photon. That is the lowercase Greek letter gamma, because gamma rays is a ray of light. There's radio, electromagnetic, infrared, visible, ultraviolet, X-ray, and then gamma ray. Fun fact, the dude who discovered X-ray called it X because he didn't know what it was. But anyway, the gamma ray is why it's called gamma, because the Greek letter for gamma is that. And I don't know the relation between the capital. Like, usually in English we have that, and well, that doesn't make any sense either. But C and C, D and D. Never mind. That was a horrible argument. But anyway, uppercase gamma, lowercase gamma, and there's alpha radiation, beta radiation, and gamma radiation. Gamma has to do with photons, which is why that's the symbol for it. Anyway, enough of that. The photon, like the gluon hangs around quarks, the photon hangs around electrons, I think. Anyway, the photon is the particle of light. It's the particle that acts like a wave. No, acts like a particle but moves like a wave. And like the gluon and the photon are related in that they have no mass. They are made up of matter, but they have no mass at all. It's weird. Quantum physics is weird. Anyway, the photon is responsible for electromagnetic charges, I think. Yeah, that's why it hangs around the electron. And these, too. These don't have charges. Neutrinos don't have charges. But the electron, muon, and tau leptons all have -1 charges. And the quarks have a specific charge, too. So that's why the photon is the reason for that, because it's electricity, magnetism, and light. Light, electricity, and magnetism are caused by the same thing. So anyway, next we have two bosons. The Z boson is called Z because they were planning on making that the last boson, but then that has a 0 charge. All the bosons have no charges. They call that the Z boson. Very creative. Oh my god. At the Z boson, very creative. And then they discovered, I don't know why they call this the W boson, but it's basically a fatter version of the Z boson, plus it's charged with either positive or negative. But anyway, these things, well, let me just do this as the representation of that. These things go in and they can change an up quark to a down quark. Let me just, I don't know what, I'm trying to draw like a thingy here, but they change an up quark into a down quark. And, you know, and then that would change a proton, an up quark, down quark, and up quark. They can change the up quark into a down quark, which would change the proton to a neutron, and then the proton would change it to a neutron, and then the atom would not have the correct amount of protons, so it would be missing a proton, and the number of protons determines the number of protons determines the element it is. So if a Z boson or a W boson hit an up quark and change it into it changes it into a down quark, then it changes the neutron, it changes the proton into the neutron, which changes the element. So if this thing gets in your atom, it's going to change the atom. It's going to change the element. So, and this is called, I neglected to tell you what this was called, the weak nuclear force. And it is weak. That's why it's called the weak nuclear force. Now we get to the fourth force. Gravity. Now, there's no... That was supposed to be a G. This would be called the graviton, except it doesn't exist because... I don't know how to draw Einstein's face, but Einstein said that gravity is caused by a mass warping space-time. So, plus, we have never found a graviton. And gravity is... I don't know which is stronger, the electromagnetic force or the strong nuclear force. I don't know which one's stronger, but those are the two strong ones. The weak nuclear force and gravity are the two weak ones, and gravity is the weakest. Gravity is by far the weakest force in the universe, and scientists don't know why, because it is so effective. Flat earthers, that's gravity, son. Anyway, it's so effective, but it's so frick. Anyway, it's so effective, yet it's so weak in the quantum world. So that's baffling scientists currently, and they're trying to look for the graviton. But I personally don't think the graviton exists. But the thing that causes mass, and it was sometimes particles are theorized before they are discovered, and the Higgs boson is called Higgs because I don't know what his first name is, but his last name was Higgs, and he discovered this, or theorized it. People are coming in the house, so I might have to move upstairs. So bye. Oh, it's so freaking nice outside, Okay. The last particle that we have today is the Higgs boson. And they say that the Higgs, there's multiple of these particles, by the way. There's not just one. The Higgs boson tells other particles what their mass is. Now, it doesn't specifically tell them and let them know how much they weigh. It doesn't work like that. It tells you, and it doesn't give them their mass either. It doesn't give them their mass. It interacts with its Higginess. It interacts with its Higginess here, and makes the particle weigh. So if the Higgs boson didn't exist, all of our particles would just be floating weightlessly. And these particles are the reason that that our mass makes a difference on how much we weigh. So the Higgs boson is the closest we have come to discovering the particle of gravity. Now, it doesn't cause gravity. It simply helps things obey gravity. So, yep. This is my school journal, so I gotta rip all these pages out now. Okay. I hope you enjoyed learning about subatomic particles. Let me know if you have any questions, or if I missed out anything, I got anything wrong, or, let me know a future subject I could talk about. Let me know what you think quarks might be made out of. But yeah, that's all the elementary particles that scientists have found, minus the graviton. So yeah, bye.